So I forgot to write down the name of chapter 11, but chapter 11 is something like bulk methods. And so we're now going to talk about the concept of bulk electrolysis. And so up until this point, right, I've told you, when I tell you we're going to make some assumptions, I've told you we're going to assume that we have a tiny electrode in a big swamp of analyte, right? And that whatever reaction we do with the electrode, it never affects the bulk concentration. Well, what if, instead of that, you want to actually try and use up all the analyte in solution, right? So that's kind of like what we're talking about now, bulk electrolysis. Well, there's a couple ways to go about it, and we're going to skip the whole chapter, except for we're going to get to section 11.7. And in section 11.7, they talk about a trick that is not so tricky, but that you could think about, right? So if you have a tiny electrode in a big solution, you say, I want to electrolyze the whole thing. Well, that kind of sounds hard. But what if you just shrink the solution compared to the size of your electrode? Oh, that sounds like a great idea, right? And so they talk about what's called a thin layer cell. And so the idea of a thin layer cell is this, right? This would be your electrode. On the other side, you have a cell, something that makes a cell. And I purposely drew it so that the diameter of the cell is very small compared to the electrode. So if a molecule gets in here, right, what are its chances of diffusing out? Not real good, right? I mean, it's pretty well trapped. It's gonna have a very small pathway to get out, especially if it's like in the middle. And so the idea again is that we're going to trap our molecules in this cell, and then we have a large sort of area, or at least dimension, compared to the volume. Okay, so let's talk about what would happen then under electrolysis. Let's talk about, we should be able to like use our stuff up. So we ought to be able to get some sort of limiting condition, right? And the limiting current. Let me function of time. And so it will be related to, we always have N and F, a number of moles of electrons times F. It'll be related to the current we're getting, right? How many moles we're consuming. Right, so big N, I've got this number of moles coming. So that's the number of moles that we're consuming, right? So that makes sense, how much current I'm getting, right, is a flux, how much gets the electrode. In this case, we're not so worried about the area of the electrode, right? I'm more worried about how many molecules did I trap in my little cell. And so how many molecules did I trap in the cell? Well, we can write an equation saying the concentration, right, would be equal to a number of molecules divided by big V, which is volume. And as I continue to write equations, it's going to be volume, just so you know as we go through this part. I know it's not voltage, so I'll point that out, right? So this is freshman chemistry, you knew that, right? Concentration times volume equals the number of moles. Good. And so, right, we could substitute this back into our current equation, right? That this would be equal to NF volume times dC dt. Okay, so the current that I'm going to get, just again now depends on, the rate that I'm, the concentration is changing, which depends. So how fast is the concentration changing? Okay, we have to kind of come up with an expression for that. And basically, there's two equations you would do to get that. Right, so we know the bulk concentration is going to be equal to the concentration of O plus the concentration of R. So remember, in the rest of the examples, we never really talked about this before, right? But in this case, let's say we start with all O. I start with like micromolar of O. Well, half of it goes to R, right? So now I have half O and half R, right? It's still micromolar, but half of it's in the form of O and half micromolar of O, half micromolar of R. That's going to equal the total, right? Because we're doing a bulk thing, we're hoping to use up all of it. So we can use that, all right? That equation is easy. And then what's our equation that relates potential to concentration? I'll take a name for a very famous equation. No, that's potential to voltage. You use this since freshman chemistry. The Nernst equation. All right, so we need the Nernst equation. Again, we can't forget things all right, so we have the Nernst equation, right? Right, and then the Nernst equation is going to have in it concentration over concentration. Right, so we have these. We can relate them back to the bulk concentration that we put in. And so, if you did some magic hand waving, you could combine these two equations, and I'm going to combine them, but this is kind of it's one of the very few. I decided to do this derivation today. It's one of the few equations I'm looking at because I wanted to show you something. So this part is really unimportant. You could look it up in the textbook. I just want to show you something. So you end up with an NFRT times E minus E0 prime. Make sure that whole thing is 1 over. All right, so you could do that. I tried actually. It's not that hard to do. I always like to do them on my side. So you could do that. You could combine these two equations, right, and get them into that kind of format. All right. So I did that, right? And so now I want to put it back into I, right? So I need to know what's dc dt. Right, this one I didn't do. So if I'm going to take the differential of one side versus time, what do I have to take? What's the variable I want to take the differential with respect to time on the other side? All right, bulk concentration, that's a constant, right? N, that's a constant. F, R, T, those are all constants, right? So the only thing that's on the other side, right, that's going to be changing with time is potential, right? So I want to take this and get a derivative out with respect to potential. Again, no, I'm lost to do that in my head. But you see that's why I'm going to rearrange it. The only other variable is potential. The only thing that's going to change is with respect to time is potential. So what drives the concentration change? Potential change with time, right? dE dt. And so, again, we'll get that out of there. But then, turns out we can look at a definition for dE dt. And the definition, again, just due to semantics of signs, there's a negative sign in there. But what's this? The change in voltage, right, and the change in time. We have a name for that, right? That's called the scan rate. So how much we change the voltage, sorry, not volume. Maybe I should have written it as E. How much we change the voltage over time is the driving force, right, for how much we change the concentration over time. It's the only things in the equation. So I want you to see that, and I'm pushing that because we're going to get to, this is one of the hardest ones to understand, why this is sort of dependent on scan rate. So again, potential is the driving force for being able to change the things. And so if we assume E is equal to the formal potential, and we take a derivative on that side, and we solve, we end up with this. N squared, F squared, little v, big V for volume, concentration of everyone's bulk, over R, 4RT. So this is the peak current that you get in a thin layer cell. So if you're going to use it all up in a thin layer cell, then the peak current is now dependent on scan rate, right? And so that's different than the equation we did in chapter 6, right, which was the diffusion control equation, where I peak was dependent on the square root of the scan rate. So here, again, it's dependent on scan rate because it's the ET that's the driving force for how much concentration is changing. And so, again, when you put that together, that's why it's dependent on scan rate. It's not dependent on how fast it can get there. That's a t to the minus 1/2, t to the 1/2 process. Instead, it's just dependent on the driving force, and so the potential, change, i.e. the scan rate, is the driving force behind the reaction. Okay, so you might be asking yourself, why the heck is she talking about this? We don't do thin layer electrochemistry in this lab. And it's true, we don't. We don't do thin layer cells or anything like it. But it turns out that thin layer electrochemistry theory is the same theory for adsorption theory. So let's, instead of thinking of a thin layer cell, instead of that, where I trap all the molecules and they can't get away to the surface, now let's think about the ultimate trap. I trap them because they stick them, right? And then you can think it's the same theory, right? They can't get away. So what's going to drive the concentration change? You can imagine it's going to be the same theory, except, it's going to be the potential, the potential change over time. dE dt is the driving force between how much concentration changes with time, which is how you get out kind of the I thing. Okay, so now I've jumped on you because the thin layer cell was chapter 11, and then we're going to do it all again. But we try to skip to chapter 14. So now, instead of being a thin layer cell, as I said, it's going to be adsorption. So now we're going to look at our electrode, and we're going to look at it when our molecules stick to our electrode, and they absorb to it. Okay, so let's go ahead and I feel like I want to do the equations first because we just did them with thin layer cells. All right, so we need to define a variable gamma, capital Gamma, not hanging. And this is going to be our surface coverage. So basically, it's going to be like in moles per centimeter squared. So that's our surface coverage. So how much is on the surface? And so similar to stuff I probably just erased, maybe not. Right, the surface coverage of O plus the surface coverage of R, right, should be equal to whatever our bulk surface coverage was, right? So 5 molecules, that's a bad example. 10 molecules absorbed, right? Well, 7 of them may be O, or 3 of them may be R, right? But they're all 10 have to be accounted for. Okay, remember we just wrote that equation for concentration in the bulk, except now it's just, think of this as like concentration on the surface, right? How much is on the surface versus in the bulk? Well, the same thing applies. We can still write the Nernst equation, right? So we can still have this. All right, that hasn't changed. But I have a slight problem. I haven't told you how to relate surface coverage to concentration. How? Oops, we haven't done that yet. All right, we gotta do that. So it turns out that you can write an expression in the book they call beta. Again, they're back to the thermodynamics thing, so instead of using O for the molecule, they use I. Don't ask me. Same thing, I don't care what the subscript is. So this is for the molecule I, is equal to the exponential of minus delta G, that's with the bar, over RT. So this, again, when we put the bar on it, remember that became our kind of electrochemical. This ends up being the free energy for adsorption. And so we have some sort of thing. And so we end up kind of ending up with an activity, i.e. a concentration of I adsorbed is equal to a beta times the activity of I that's in the bulk. So this big A is supposed to mean absorbed, and this B is in the bulk. So that gets us basically these back and forth between concentration adsorbed, the book says it in activities, whatever I could have. Concentration adsorbed is equal to this beta constant times that. They do a little hand waving in the book and put a few more constants and stuff in that are confusing. But that basically gets you back and forth. And again, you could write out lots of equations for adsorption, et cetera, and they would all basically relate you back to this beta as far as that goes. And so if you were to do that, and then you were to solve this equation once again, you would get this. N squared, F squared, V, 4RT, that's all the same as the last time. The thing that's changed is this term. Of course, I erased it from the thin layer cell. But for the thin layer cell, we had a volume times concentration, right? Volume times concentration, number of moles. Now we have surface area electrode times surface coverage, right? Surface area times surface coverage is number of moles. So it's the same equation. That's why we do the thin layer cell, because it's actually easier to think about it. But this is the equation that governs adsorption, right? Where I peak for an absorbed species is proportional to scan rate. And so it's hard to explain. As I jokingly say, if you ever get this question, start with diffusion and hope they don't ask you about absorption. Because it's not the easiest one to kind of come up with the answer of like, why is that kind of thing, as I said. But there's really two things that I think that the biggest thing that I always think of is that dE dt is the driving force to drive the concentration change, the dC dt, and the dC dt, again, that change is what's going to give you our I. And so, as you sort of start to think about it, I think that can make some sense. Sometimes people use another word for this. And so they'll call currents for absorbed things pseudocapacitive currents. Why would they do that? Well, it turns out capacitive current, I skipped over back here. But capacitive current is proportional to scan rate. So capacitive current is equal to a scan rate times area times the capacitance of the electrode. Right? So, and you've seen this, right? Your gain changes as you go faster. Or if you go really slow, you might have to change the gain setting. And so it's the same sort of idea that the driving force, again, that rate of change of the potential that you're applying to the capacitor is greater, so the rate of change of the charge buildup basically is different. And so the driving force is dE dt for both of them. So some people think it's easy to think of it as a pseudocapacitive current. Other people probably don't like that sort of terminology and how to think of it as a capacitive current. Let's think for a second. Put on our thought caps again. I don't like to teach equations without thinking about them. If you don't think about them, again, this is a point in lecture where I was going to say, if you spew these equations on the board during your orals, don't think that they're just going to be like, yes, they just wrote a complicated equation on the board, that's all I wanted from them. What they really want is for you to somehow do what I've been trying to do in words, which is explain it in words what's really happening at the surface of the electrode. So equations are nice, but memorized equations will not pass your orals. They would much rather you start to talk about, well, absorption equation is a lot like capacitive because you know, capacitive. It's the driving force of how, you know, the change in voltage over time that drives, you know, how many electrons pulled up, you know. If you start with that kind of explanation, you're far probably better than just spewing out, well, I write the two equations on the board, and ours follows this equation, and it doesn't follow the other one I threw up, thus it's absorption controlled. And they're going to be like, well, I don't know that he has any, or she has any physical understanding of what's going on. Although, you know, quite frankly, I've never seen anyone fail that wrote up all these equations, but that's usually because by the time they memorize them, they actually understand. I have seen people fail their worlds because it happens more often than I would like to say. And I always look at it like this. I taught it to them. You know, they should have known it was coming. This is the kind of stuff that people are asked about, like, oh, only maybe 80% of people get this question, right? You know, and I know they know it ahead of time. So if you can't come up with good answers, can't answer these kinds of questions off your feet, then, you know, it's the kind of thing you should be prepared cold to explain to somebody. So practice with each other. Practice explaining it on the board to somebody. Practice explaining it out loud to somebody. You know, why is your experiment like that? And I actually try and help you do this. Because when you're first doing things, like when you come to the Monday meetings, sometimes I'll ask you, well, why is that? You know, I'm trying to get you, you know, and sometimes people go, I don't know. And that's okay. Like, you know, someone told me this experiment, they have no idea why it should be like that. But, you know, I don't want the answer to always be, I don't know. You know, I'm trying to give you the chance, you know, if you give a group meeting, so you have group meetings coming up, and you say, oh, I'm only going to explain those experiments that everybody knows. That's okay. Explain it to us with gusto. You know, what's going on? You know, why is it scan rate like it is? You know, kind of thing. We can all use that reminder. You know, I want to hear good explanations, because that's good. That's what people are going to really want to think about. Okay, so that's the equations. Let's go back and think about why things absorb for just a moment. So let's go back to the surface. So we typically have like a carbon surface on our electrode. And it's not flat, so I'm trying not to draw it as flat. Right, and our carbon surface though isn't really